yeah, so all right, so today I'm going to talk about hypergraphs, co-optimal transport, which is a metric for hypergraph, and then there's some category in there. That's why it's maybe relevant to provide this workshop. First, I'd like to thank my co-authors. Yoja and Ethan are PhD students, and then Samir and Tom, and my founding agency, NSF and DOE. All right, so we do have a write-up on arXiv. You want to take a look. It's currently under a little bit of revision, so over the next month or two, we'll probably update a newer version. We also have source code online, and you can play with. And also a few pictures from this talk is from my other work with Emily and Achet that has visualization of hypergraphs. So the high-level picture is that the talk I'm giving today is at this very nice intersection that I'm quite excited about. It's intersection between optimal transport, data visualization, and of course TDA, and with a little bit category series thrown in the mix. So let's start with hypergraphs. Hypergraph actually arise from quite a different type of data. People are familiar with co-author networks. Usually co-author network can be modeled as hypergraphs. Here's an example where it's a gene biological pathway hypergraph where each node is a gene and each hyper edge in this case is visualized as sort of those kind of convex holes that include the black dots. Those are hyper edges. So before I go on, I like to kind of familiarize everybody with sort of my visual encoding here. So I can visualize a hypergraph as what's called an Euler diagram, which is basically treating each hyperedge as a set, and you're just looking at set relations. So each node is an element or a vertex, and then each of those convex hole is a hyperedge. And in the middle is actually two equivalent way of visualizing hypergraph as a bipartite graph. So on the left-hand side are the vertices, the right-hand side, the colored nodes are the hyperedge. There's a connection when one is a member of another. And then finally, I can actually take this hybrid approach, which is basically visualize the hypergraph as an Euler diagram, except I also want to highlight the relation between nodes and hyperedge. So in here, I'm using colored node as a hyperedge, but also colored convex hole also as hyperedge. And then there's a little bit connection between, so just to highlight their bipartite relation between them. So you're going to see this visualization quite a bit throughout the rest of the talk. So what we're looking at first is a distance between hypergraphs. And then the motivation behind it is that such distance also provide a hypergraph matching. When I mean matching, I really talk about this sort of matching between hyperedge into one another and matching between nodes into one another. And then this is all done through a probabilistic notion. And we'll come back to this example very soon. So the high level idea is that this distance we're looking at is really looking at optimal transport between the hyperedge as well as optimal transport between the vertices or the nodes at the same time. So on the high level, in order to define such a distance, we're really thinking about probability measures over the nodes and hyperedges of the hypergraph, and also some relational information that capture local and global structure. When I say relational information, is what's the relation between nodes and hyperedge. So for that, we kind of define what's called hypergraph distance that is based on what's called co-optimal transport. And then once you have this distance, you can also study the category between hypergraph and the category between graphs. And then essentially when I take a hypergraph to a graph, what is the functorial properties and what is the Lefschetz bounds, which I hopefully will make clear very soon. Now, there's a lot of hypergraph metrics in the literature. For example, the MS distance back in the 1977 is related to sort of a distance between clusterings. And some of them is based on sort of study of subgraph isomorphisms, which are typical NP-hard. So instead, our framework does not require the hypergraph to be defined on the same set of nodes, so they don't have to be of the same size. It has nice metric properties, and I would argue it kind of encode more structured information through the sort of probabilistic notion, and it also gives meaningful matching results between hypergraphs. There's a huge amount of literature in optimal transport. So here is only a subsample. I can't really do justice in a short talk, but I listed some of those more recent advances in optimal transport. The one on metric measure space, the one on optimal transport metrics. The one that is most relevant to us is sort of looking at the work by Samir and Fagundu back in 2019, which look at Gromov-Washington distances of graphs. And then the one we also rely heavily on is the co-optimal transport work 2 years ago. Okay, so let's just get to the meat of things. In order to talk about the category of hypergraph and category of graphs, we actually kind of generalize the notion of graphs and hypergraph to what's called measured networks and measured hypernetworks. And here, this is sort of Samir and Fagundu actually studied this quite a bit in terms of measured networks. So this is just a quick review. If you think about a graph, it has a set of vertices and set of edges. Now, if I want to generalize it in a probabilistic notion, then what I would work with is what's called measure network, meaning that you can imagine X is sort of a polished space, mu is a Borel probability measure on X, and omega is sort of a relation that talks about elements, a pair of elements, and map to a R. This is what we call network function. But in terms of graphs, one simple example is here. In this particular example, I have a graph with 4 nodes and 5 edges. I can think about X to be sort of my node set. That's just 4 points. And then my mu is a uniform measure on each of those nodes. So it's 1/4. And then my omega is really capturing the relation between pair of nodes. In this particular case, I'm going to use omega as some sort of adjacency. So node 1, 4 is adjacent to each other, so it's 1, and node 2, 4 are not adjacent to each other, so it's 0. So this is one very simple way of encoding this graph as a measure network. Now, once you have, and then another additional thing I want to talk about, just a quick review. If you have a probability space X mu, Y nu, there's a coupling, which is basically a joint probability measure on the product space, such that its projection into each individual space is agreed with the original measure. In some sense, think about this essentially as the marginal distribution. So this comes up when we look at the next slide. So when you have a measure network, you can define what's called Gromov-Washington distance between measure network. So again, you have a pair of measure network. You can define the distortion, which is basically looking at the omega, which is network function to the piece power, and then over sort of the coupling between the nodes. So the GW distance is essentially try to find the optimal coupling to minimize the distortion. So effect of this distance really in our current context is that if you achieve the optimal coupling, it gives a soft matching between the points in the measure network or nodes in the measure network. Okay, so this is sort of fairly classic sort of optimal transport kind of formulation. Now, what I want to move on is how do I think about hypergraph in this measure framework? So remember, a hypergraph is a set of nodes and a set of subset of nodes, which are called hyperedges. And what we call a measure hypernetwork is now have 5 elements in there. So X mu, think about this as sort of nodes and measure on the nodes. Y nu is set of hyperedge with measure on the hyperedge. And then the omega is again what we call hypernetwork function, which is again taking a node and a hyperedge and give a relation. So let's just do an example. hypernetwork can arise from other data other than hypergraph, but for this talk, I'm just going to focus mostly on hypergraph. So again, let's look at the hypergraph you saw before. In this particular case, I have 5 nodes. So each one of them, let's use uniform probability measure. So it's 1/5. I have 4 hyperedges. And again, I'm going to do uniform measure over the hyperedge. And then the omega, for simplicity, I can do what's called incidence relation, meaning that, if an edge is part of the hyperedge, then, the row of this is all the sort of nodes, and then the column are all the hyperedge. So there's a 1 if the node belongs to the hyperedge. But you can also do sort of shortest path relation, which is the length of the shortest hyperedge path from any hyperedge that contain the current node to another hyperedge. So that's another way to encode the information in the data. So if you look at this formulation, there's quite a bit of flexibility in how you model a hypergraph as a hypernetwork. You can vary what's the probability distribution. So if you think about certain node to be important, you might vary this probability distribution over the node. You also can vary probability distribution over the hyperedge, depends on prior information, and you can change this omega, which describes the relation between node and hyperedge. So you have a lot of flexibility in model your data this way. But what we really care about in this talk is what is sort of a distance between sort of hypernetwork. So if you have 2 hypernetworks, again, you can define a sort of a distortion. Again, the distortion is sort of the hypernetwork function to the piece power. So this is sort of, or you can think about omega as sort of a weight matrix to the piece power. And what's interesting here is you're looking at the coupling between nodes and coupling between nodes and coupling between hyperedges. So the sort of hypernetwork distance is looking at all the optimal coupling between the nodes or the optimal coupling between the hyperedges that reduces the distortion. So this is actually a direct extension of the co-optimal transport framework. And then the interesting part in terms of computation is you are looking at optimal coupling, between the nodes and between the hyperedge at the same time. And then essentially, once you can compute this, what it gives you is a probabilistic matching between your nodes and hyperedge. So this is a picture I want to come back to. So in this particular case, I'm varying my probability distribution so that it has to do with degraded information, and then the omega has to do with J-car indices. But that's sort of more secondary. I just really want to show what do I mean by probabilistic or soft matching between hypernetworks. So on the top, I'm looking at the coupling between the hyperedges. So this is a sort of the matrix that showcases the coupling. Let's just focus on specific element in this coupling matrix. So I have on the first hypergraph, I have 4 hyperedge, that is A, B, C, and D. The second hypergraph, I have 3 hyperedges. So they are probabilistic matched in the sense, let's look at node. In this case, let's look at node A in the second hypergraph, which is corresponding to this particular hyperedge. What this coloring is saying that a quarter of the mass is coming from the orange hyperedge, and then sort of 3/4 of the mass is coming from this green hyperedge. So in terms of probabilistic distribution, it says this is coming from orange, and this is coming from orange, this is coming from green. So essentially, there is a probabilistic matching between the hyperedges. And that's what you get from the first coupling matrix. Similarly, you get a second coupling matrix, which is a probabilistic matching between the nodes. And those coupling are achieved at the same time. All right. Okay, so I really want to move on to the categorical part, but let's just talk about, high level, what are the properties of this distance. So I have this hypernetwork distance, which is based on what's called co-optimal transport. Under this is actually a pseudo metric over the space of hypernetworks. And then you can define something called strongly isomorphic between 2 hypernetworks, is that if there's a bijective measure preserving maps between the nodes and hyperedges, and the omegas, sort of the weight or hypernetwork function or the weight function kind of is preserved into this mapping, then this So that means those two hyper networks are strongly isomorphic, then this distance is equal to 0. Now, we can also define something called weakly isomorphic, which is precisely if I have two hypernetworks, if their distance is 0, we call them weakly isomorphic. So of course, if I quotient them out, basically treating all the space of weak isomorphism class of measure hypernetwork to be the same equivalence class, then this is a metric over this space, their quotient weakly isomorphic classes, and this space is complete and geodesic. So I mean, takeaway message is this distance give me nice has nice metric properties. All right, so okay, finally, let's talk about a little bit category stuff over the next 10 minutes. So really, one motivation, there's many motivation of study a metric between hypergraphs. You can do classification, you can do clustering, you can do comparison, you can do matching, and so on. But one of them is to give a language to study the mapping between hypergraph to graphs. So oftentimes, when people study hypergraph, one way they do it is to map a hypergraph to a graph. And this way to kind of simplify the underlying structure, and it has some tractable properties. And here's an example of a few representation of hypergraph as graphs. So this is the original hypergraph, and then B is the bipartite representation of this hypergraph, and C is what's called a line graph. And D is called the dual hypergraph. I will explain line graph very soon, but D is dual hypergraph. A dual hypergraph is just sort of exchange the role between hyperedge and nodes. So a nodes become a hyperedge, and an edge between a hyperedge between a node. It's basically taking the transpose of the instance relation. And then E is what's called clique expansion. So E is also the line graph of the dual. So what do I mean by line graph? A line graph is essentially looking at intersection relation among the hyperedges. So I have 4 hyperedge right here, and I turn each of those hyperedge into a node in my line graph. And then if 2 hyperedge has non-empty intersection, there is an edge between them. So another way you can think about it, it's kind of like a nerve of, if I'm thinking about hypergraph as covering of underlying space, this is sort of the nerve of it in a way. Okay, well, actually it's the one-dimensional skeleton of the nerve. Now the bottom is the dual hypergraph, and if you take that line graph of the dual, it's what's called clique expansion. So those are, so B and D are some of those other ways of mapping a hypergraph to a graph. So where does the category thing come from is that we actually want to study the category of hypergraph mapped to a category of some sort of graph and study sort of the property of the functor. So, okay, so of course now we have, well, everything is formulated in this measure hypernetwork language. So I have category of measure hypernetwork and category of measure network, and then then the trick is how do we define a specific morphism? So so the idea is follows. There's many type of morphism I can define between measure hypernetworks. So let's just look at a few of them. So the first type is what we call expansive category. So the morphism is basically corresponding to edge containment. So if I have 2 elements in this category, each of them think about coming from hypergraphs, then so first of all, I need to define the morphism so that, if I go from this hypergraph to this hypergraph, it's actually preserve the containment relation. For example, if vertex X is in some hyperedge, then through this mapping is also it's also preserve the containment in the relation. So, a very interesting thing is that if the underlying number of nodes is the same, and then if this is identity map, if we study the map of cover that arise from multi-scale mapper, this can be thought about as a specific morphism that I care about. Now, the expansive morphism is really saying that, I preserve the relation, but most importantly, my hypergraph function is strictly increasing. So, well, a simple example, of course, is when omega is instance relation. So if X is element, if a vertex is an element of a hyperedge, through this mapping, the corresponding image is also an element of that. So in a way that whatever is incidence in the original hypergraph in the image is also incident in the mapped space. So that's one way of thinking about a very simple example of expansive category. There's of course other examples, but the important part is that we're going to use E to represent all the expansive morphism. The second type of category is thinking about the morphism between two hypernetwork such that they are measure preserving. So a measure preserving morphism between a pair of measure network is a pair that maps the vertices and map the hyper edges such that all these maps are measure preserving. So under measure preserving morphism, you can talk about measure preserving category of hypernetworks too. So the idea is, and also finally, we also have this dual version, right? Remember, I can take a hypergraph and take its dual. So you can also think about there is a dual hypernetwork with a giving measure network. Giving a measure hypernetwork, there's a dual version of it, which is basically just switching the role between the edge and hyperedge. So the first type of thing you can study is that if I take the dual map from a hypernetwork to its dual, then this specific map is a covariant endofunctor for both expansive and measure preserving category, and is also an isometry. So I mean, on the high level, what you want to think about is that when I take a hypergraph to its dual, then the space of hypernetwork and the space of dual hypernetworks, through this mapping, the actually distance is preserved. Not too surprising. Now, when I'm thinking about the really mapping from the category of hypernetwork to the category of networks, or thinking about it mapping from the space of hypergraphs to the space of graphs, we really want to study sort of this particular functor, and we want this functor to be well behaved in the sense that we call this sort of a graphification if this map is Lipschitz with respect to distance in both space. So in a way that you have sort of in here, this is the distance in the space of network. Here is a distance in the space of hypernetwork. You want to, when you map from the space of hypernetwork to the space of network, the underlying sort of distance does not have too much distortion. So this kind of thought applies to all three settings. The first setting is to look at the space of hypergraph to its space of bipartite or incidence graph representation, the space of hypergraph to the space of line graph, the space of hypergraph to the space of clique expansion. So you are always, in some sense, in the categorical language, studying the category of hypernetwork to the category of network, and you want that functor to be well behaved. Okay, so this kind of put this into a nice language whenever someone is mapping a hypergraph to a graph and try to study the space of graph, you want that mapping to be well behaved so that, you know, whatever property you derive from the graph is somewhat related to the property related to the hypergraph. So now what I'm going to go through, I think I have 2 minutes, but let's see how I can do. The idea on the high level is if you look at the space of hypernetwork and map it to sort of the binary version, and then there's a specific way to design how the hypernetwork function is, then you can show that under a specific way to design the probability distribution as well as the relation between nodes and hyperedges, you can get the result that this map, you know, mapping from this category of hypernetwork to the category of binary incidence networks, it's a sort of proper graphification with Lipschitz constant equal to 1 in the both expansive and measure preserving category. So this is good, meaning that if I take the binary operation, there are settings where I don't sort of morph the underlying space too much. Now, the second part is, I'm going to skip this. This is a little bit too much, but the second part is I want to study how one map from hypergraph to the category of graphs. It turns out if I want to preserve the Lipschitz property, I actually need to be a little bit careful how I am designing the probability distribution and then specific the omega. So essentially, what we typically think as a naive way of mapping with this relation of omega here and omega here, if you're not careful, it's not a graphification functor. But instead, what I'm going to show is that if you actually modify this mapping slightly, meaning that when I map the hypergraph to a graph, I need to look at how this weight is changing, and I need to do this form that is actually almost look like a normalized graph Laplacian. Under this specific type of mapping between the hypernetwork and a network, you actually can get Lipschitz condition. So essentially, if we the take-home message is that when I map the space of hypernetwork to the space of network, if I'm careful over how I'm mapping the relation between nodes and hyperedge through the omega hypernetwork function, then this is graphification with Lipschitz constant square root of 2, and then this applies to the category of measure preserving category. Okay, so sorry, I flies through a little bit, but then of course the same thing will also apply if you are careful how you map the sort of hypernetwork function. You can also show that there is a nice graphification from the category of hypernetworks to the category of clique expansion. Okay, so there are some experiments you can do with this metric. You can do clustering. So if you start with some synthetic hypergraphs, you can use this metric to show clustering based on the underlying parameter. You can do shape matching. In fact, multi-scale shape matching. If you're interested, we can discuss this offline. And then this is related to multi-scale mapper in a way. So you can map sort of two mesh in high resolution and low resolution at the same time, where the low resolution mapping is essentially the a derived sort of the line graph of the high resolution mappings through covering. And then, yeah, so looking ahead, I think this is a very nice landscape of studying the space of hypergraphs, but also studying the relation between hypergraph and graphs. There's a lot of interesting questions in this space. Another way that is more related to study of category, you can also think about what's called hypergraphification, which is mapping graphs to hypergraph, and study the category of graph mapping to category for hypergraphs. So that's left for future work. Anyway, that's it.
Okay, thank you, Bei. Any questions for Bei? Oh, there are many questions. Tamal?
Oh, hi, Bei. I missed what was the definition of the distance for network you were taking here?
Oh, yes. So for network, it's optimal transport, and for hypernetwork, it's co-optimal transport. So this is the distance between hypernetwork. Let me go back to the network. Right here. Right here. So if you have, this is measure network, right? And then you have the omega, think about omega to be the simplest form is instance relation. And what you are seeing here is you define what's called a distortion, which is how far omega, if I find a coupling between the nodes of say the graphs, what is the sort of the piece power of the corresponding weights? And then this is sort of the optimal transport formulation to say that the GW distance between the measured network is the one that minimizes distortion over all possible coupling of the measure on the nodes.
So I was just wondering, how did you compute in practice this? Because
yes. Yes, so the computation, which we actually have code for, is actually coming from the code of the co-optimal transport. So all this can be formulated under a formulation of gradient descent. So what you achieve is, in some sense, a local minimum of the, and then it's in the worst case, roughly cubic time. So yeah, think about gradient descent is your best friend here, but you can't guarantee you'll always achieve the absolute optimal.
Mm-hmm. Thank you.
Hans?
Hi, Bei. I just want to ask if you've considered using this framework for graph neural network or other learning problems.
Yeah, so there's actual slides I commented out, I didn't show. The hypernetwork does not have to arise from hypergraph. The hypernetwork is a very generic model of data. In fact, what you can think about is that X can be, for example, your high dimensional data in a neural network, and mu is a distribution over your data. And then Y can be your parameter space of the neural network, and nu can be a distribution or prior assumption over the distribution of your parameter. And omega can be basically the family of machine learning model that couples data and parameter. So that's one generalization. The other generalization, as you mentioned, that if I'm thinking about, I guess you are specific thinking about graph neural network, right? So
yeah, I'm interested in hypergraph, learning classification problems on signals over hypergraphs. So I mean that's very computationally difficult to do, but maybe if you can put the right measure, I would assume, on the hypergraph, then you can accomplish this task with a graph neural network, which is very efficient.
Okay, so you are thinking about sort of the later work when I'm thinking about how do you map from the space of hypergraph to the space of graph. And if you design that mapping carefully, that specific functor carefully, then you preserve some properties. The high level picture is, yes, I think it's hopeful. Specifically, I think which one works best, it's probably is very much dependent on your specific data at hand. But I think it's a very, I think there's a lot of interesting open directions this can go. And I think on the category comments, my main comment is when people study the category of graphs or mapping the space of hypergraph to the space of graphs, they have to be careful how they define that functor so that it's, for example, what we call graphification is a type of functor that preserves certain Lipschitz condition. So if you can define in your setting from a hypergraph neural network to a graph neural network, a proper functor that preserves property with some Lipschitz condition that may lead to some nice, I don't know, this is a far-reaching statement, but the hope is that, I guess what you're saying is the graph neural network will produce results that is similar to what hypergraph neural network's result is going to be.
Yeah, that would be the hope. We should talk about this offline, but thank you, Bei.
Yeah.
Okay, so we have maybe one quick question, Tao.
So I'm just wondering, like, why don't you consider, or what's the difference of considering simplicial complexes here? Because in my understanding, like, you can take the closure of the hypergraphs, basically it's a simplicial complex. So
Oh, no. Actually, I would think about the other way. I always like to have this picture in my mind where I like to think about a hypergraph to be an incomplete simplicial complex, but a simplicial complex is always a hypergraph.
Yeah, sure, I know.
So this framework, well, okay, we have to be careful here. This current framework works for hypergraph. If you really want this current framework, in fact, actually, when we first work on this GW framework for hypergraph, we actually started by doing GW distance for simplicial complex. My argument actually over the past few years, I actually think more data arise from hypergraph than from simplicial complex. Okay, it's a biased statement, but here is the argument is that if you want your data to give rise to simplicial complex, because you always want to enforce the instance relation, and sometimes the data may not have it, so you need to put extra information to make it into a simplicial complex. But in the data I showed you here, it's very natural the data is modeled as a hypergraph. So I think the current framework is fairly general, applicable to hypergraphs. But if you want to do it for simplicial complex, we actually has a good idea of how this framework will work for simplicial complex. One way to do it is to map the simplicial complex into this multi-layer or graded graded instance relation. So you think about extending the bipartite graph to say, let's say it's a two-dimensional simplicial complex. You have a partition over your vertices, a partition over your edges, and a partition over your triangles. And then you have instance relation over them. And you can, what I'm going to say is that you can still define the GW distance between simplicial complexes, and you can also possibly compute it as well. It's just you have to do, the optimization have to deal with pairwise relations in multi-level. I don't know. I think this is probably maybe a good topic to take offline, but it's doable for simplicial complex.
I'm not trying to challenge. I'm just curious. Yeah, no.
Oh yeah, no.
Thanks.
I mean, no, it's doable for simplicial complex, but you just have to